For nearly 400,000 years after the Big Bang, space was filled with a densely packed, highly pressurized plasma. Quantum electrodynamics governed the frantic collisions of particles, while general relativity dictated the continuous expansion of the space containing them. Inside this superheated environment, matter and radiation were inseparable. Free electrons and photons were locked in a constant cycle of collisions known as Thomson's scattering. A photon could only move a minuscule distance before ricocheting off an electron and abruptly changing direction. The result was a universe that glowed intensely, yet was completely opaque. To observe the early structure of the cosmos, we have to look past this barrier. We need to examine the precise physical mechanism that eventually allowed light to break free. The overarching rule of this environment was geometric expansion. Following Einstein's equations, the physical volume of space was continuously stretching. As the volume increased, the ambient energy of the plasma was spread over a larger area, and the temperatures steadily declined. This cooling approached a strict thermodynamic threshold. The balance between the intense, ionizing radiation of the plasma and the natural binding energy of atomic particles began to shift. The plasma was reaching a breaking point. The universe was about to undergo a quiet mathematical phase transition that would alter its composition entirely. As the ambient temperature approached 3000 Kelvin, protons began capturing free electrons to form the first neutral hydrogen atoms. Initially, this delicate balance of ionization and binding can be modeled by the Saha equation, which assumes perfect thermal equilibrium. But the expansion of space didn't stop. Because the volume continued to grow, the rate of recombination eventually fell behind the expansion rate, rendering the Saha equation a mere approximation. The plasma was still heavily skewed by an enormous photon-to-baryon ratio. Even as the average temperature dropped, a lingering population of high-energy photons continued to shatter the newly formed hydrogen atoms, stripping the electrons away as fast as they could bind. Direct recombination to the ground state emits a photon that ionizes neighboring atoms. Instead, electrons attach to higher energy levels and cascade downward. The 2s excited state transition resolves this by simultaneously emitting two lower energy photons, neither powerful enough to ionize another atom. By passing through this strict microphysical bottleneck, neutral hydrogen atoms were finally able to assemble and persist without immediately breaking apart. As these stable atoms formed, the macroscopic properties of the cosmos shifted. The vast populations of free electrons that had been ricocheting around the vacuum were suddenly locked up inside hydrogen shells. This chart tracks optical depth, the probability a photon hits an obstacle. Without free electrons, optical depth plummeted. As it fell below 1, radiation detached from matter. This interval, mapped by the visibility function, peaks sharply at redshift 11, defining the surface of last scattering. Within this narrow window, light and matter divorced. The thick, glowing fog cleared, leaving the vacuum of space transparent. If we step back slightly to the era just before this decoupling, the plasma was highly dynamic. Dark matter, which doesn't interact with radiation, had already started collapsing into dense gravitational wells, steadily dragging the regular baryonic matter inward. But the baryons were still tethered to the photons. As gravity pulled the matter down into these wells, the dense concentration of photons exerted a massive outward radiation pressure, pushing back against the compression. This tug-of-war between gravity pulling in and radiation pushing out generated immense acoustic standing waves. Sound waves were physically compressing and rarefying the cosmic fluid. Over hundreds of thousands of years, these waves oscillated at various frequencies. When the optical depth dropped, each acoustic mode was caught at a specific point in its oscillation, some at maximal compression, others exactly halfway through expanding. Because the decoupling happened so rapidly, the specific phase of every single sound wave was permanently frozen into the escaping photons, leaving behind a precise map of temperature variations. With the radiation pressure suddenly gone, the remaining baryonic matter was free to collapse completely into the dark matter potential wells during the pitch-black era of the cosmic dark ages. Gravity slowly sculpted this material into an intricate cosmic web. Meanwhile, the newly liberated photons began a 13.8 billion-year journey, traveling unimpeded across the vacuum. As they traveled, the continued expansion of space stretched their wavelengths, lowering their energy. What began as intense, visible, and infrared light eventually cooled into the microwave spectrum, preserving a near-perfect thermal distribution known as the cosmic microwave background. This relic radiation serves as a layered record. It provides our final image of the hot, dense early universe and our first detailed blueprint of the structures that would eventually form galaxies. To translate those tiny temperature variations into actual physical parameters, cosmologists process the map into an angular power spectrum. The location of the tallest spike represents the physical distance sound waves traveled before the light broke free. Because the geometry of space determines how a physical length translates into an angular size on our sky, the fact that this peak appears at precisely 1 degree confirms the universe is spatially flat. The subsequent data points tell us about composition. By comparing the relative heights of the second and third peaks, physicists can calculate the precise ratio of regular baryonic matter to the dark matter that was adding inertia to the early plasma. Along the far right edge of the chart, the sharp peaks give way to a smooth downward curve called the silk damping tail. This drop-off neatly matches the theoretical predictions for how random photon diffusions smoothed out smaller fluctuations just before decoupling. Polarization data provides a second layer of information. While E modes align with density fluctuations, certain curl-like B mode patterns may eventually reveal the signature of gravitational waves generated during inflation. The era of recombination stands at the exact intersection where quantum transition rates dictated the large-scale geometry of spacetime. It left behind a highly readable dataset that continues to anchor the entire standard model of cosmology.